Everyone, so this is the lab for today. If you do not have a lab paper, if you're unable to print it out, you could just grab a blank piece of paper. You can grab a piece of graph paper from the front, it's underneath the stapler, and you can just number everything as you answer it. Okay, you do not need to have this physical piece of paper. Please don't ask to leave the room to go print it out. All right, so without further ado, let's get going with the simulation. So there's the link to it. The link is easier to access if you go via the PDF available on Canvas. All right, so here's the simulation. It's a little bit dated, but it's pretty good. You got Sir Isaac Newton in this one. So if you click on Begin, all right, there's a few different things you could change here. Um, you can change the number of washers here, and you could change the length of the string by clicking on this. All right, so if I hit Start, you'll see things move around. All right. So I'll show you this in person when I'm back, but basically the spinning mass on top keeps the hanging masses hanging. If it were to stop spinning, which you can't do in the simulation, but if it were to stop spinning, the hanging masses would fall. Okay, these washers here. All right, so I'm just going to reset it really quickly. You should be able to change the mass, but it's not letting. Oh, there we go. I can change the mass. You just can't go down. Okay. You can't go down lower than 25. Okay. So let's walk through this simulation. I'll show you what to do. Just one thing about it, though, you will not be using the same numbers that I am using. So please be mindful of that. All right, so we're going to draw a top-down view of the object that's spinning around in a circle in a clockwise circle. So let's start by sketching out a dotted line for our circle, or dotted line circle. Pretend that's a circle. All right, and let's draw our object on the string. So here's my string. We'll say it's orange. And here's the object. If we were to label the radius would be the string. And we're going in a clockwise circle. So the velocity would be tangent to the circle in the direction of motion. So in this case, it would be pointing up. And the centripetal force always points to the middle, perpendicular to the velocity. That's our centripetal force. You definitely have to be good in this unit on knowing the direction of the centripetal force and the velocity. So what's the agent of the centripetal force here? What is the thing that is keeping the object moving in a circle? So if I hit start here, we can see this object moving in a circle. So what's actually keeping it in the circle? You might say gravity, but gravity doesn't point towards the middle of the circle. If I were to pause it for just a moment, pause it, that might be, the pause is a little bit delayed on this simulation. If I were to pause it here, what you'll notice is, well, the string is what's keeping it in the circle. Specifically, we would call that force tension. So tension. How do you know? Give some sort of explanation, but basically say because the tension is what keeps the ball moving in a circle. So how can tangential velocity be found here? Think about how we've done this before. You have an object spinning around in a circle. You know how long it takes to go around the circle, right? So if we use the equation, V equals d over t, the distance to go around a circle once is the circumference, 2 pi r. And the time to go around once is the period. I'll just call it t. So r would be the radius of the circle. And t would be time to go around once. So you're going to be collecting some data here. The one thing I want you to make sure you keep constant and do not change is I do not want you to change either of the masses. And I also don't want you to pick the masses I pick. Okay? So please keep those two things in mind. Once you have the masses of both the hanging object or the number of washers, so you're not changing the number of washers basically, and the moving mass, you do not change those for the entire experiment. So I'm going to reset mine. I'm going to make the moving mass 56. There it is. Okay. So I'm going to go to my sheet and I'm going to put in 56 grams, but it's got to be in kilograms. So that's going to be 0.056 kilograms. I don't need to actually label the units because the units are at the top. Okay. So what am I going to do here? I am going to pick 1, 2, 3, 4, 5 different radii. I'm going to time how long it takes to go around 10 times. Divide that by 10 to get the period. Now, why am I timing how long it takes to go around 10 times? What you'll notice is that starting and stopping this is really, well, stopping this is really hard to do to get an accurate stop, like to perfectly stop it after 10 revolutions. So what we will do is by doing 10 revolutions and dividing, we minimize that effect. Then we're going to calculate the tangential velocity, the centripetal acceleration, and the centripetal force. You just need to show one calculation for each column, but you do need to do 5 different radii. And again, you do not change the number of washers. So for example, my number of washers is 14. I will not change that. You can't use 14, and you cannot use 56 for the moving mass. So let's get going. All right. So my first one, the radius is, let's see, this is a little bit more than 1.5 meters. See, this is 100 centimeters. This would be 150 centimeters. So I'll call it, this would be 160. So I'll call it 1.51 maybe, 1.52. So let's get the time for 10 revolutions. So the simulation is pretty nice in that at least you don't need to use a stopwatch. So when you hit start, I would recommend saying to yourself 0, and that would help you to get counting. Okay, so for example, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See, I was a little bit off there, but it's all right because, like I said, that's why we do the 10 revolutions to minimize that effect, that missing the perfect stopping time would give us. So that's 15.7 seconds. So the time for one revolution would just be dividing that by 10. So our tangential velocity, we did the equation up above, 2 pi r over t, 2 times pi times my radius here is 1.52 divided by my period, 1.57. I got to be careful because those are pretty close. But again, you should be using different numbers than I'm using. So please make sure you're using different numbers. I'm going to make a little note to myself that I'm using 14 washers. So this is 6.08 meters per second. Then you would use our centripetal acceleration formula, v squared over r, to get that. So 6.08 squared divided by 1.52. I get 24.34. I don't really care how many significant digits, not too many, not too few. Now to get the centripetal force, you could either do mv squared over r or just multiply your centripetal acceleration by the mass, which is what I'm going to do here. Now, which mass do you multiply by? The number of washers? The washer's mass or the moving mass? Well, centripetal force is for objects that are moving in a circle. So it's the moving mass. So I would take my 24.3 and multiply by 0.056. So I get 1.36 newtons. Now you're going to do this 5 times. I'm just going to do one more. So what I need to do now is I need to change the radius. So I'm going to hit reset. The number of washers should not change. There it is. It doesn't. My moving mass does not change. Okay. If it did, then you have to get back to it, which can be annoying because the numbers are kind of random. It's annoying to get back to an exact number. So what do I do for the second trial? I just need to change the radius to something different. Okay. I'm going to make my radius, I'm going to make it pretty small. Right about there. I like that spot. So that's almost exactly 0.6 meters. Okay. So let's record that. Let's get the time for 10 revolutions. This one's actually going to be way quicker. So the shorter it is, the faster it's going to be. So that's why sometimes students like to pick longer ones. You have to take slightly more time to take the data, but you get much more accurate data. So let's try this one. I'm going to hit start. And again, I'm going to say 0 when I hit start. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, again, I was a little bit off. There's a little bit of delay there. So if you're good at anticipating that, you can fix that a little bit. So this is 9.9 seconds. So my period would be 0.99 seconds. Again, I don't need the units on that. So I'm just going to calculate tangential velocity like before. Here I got 3.81. My centripetal acceleration, I'm getting 24.2. And my centripetal force, I'm getting 13, or excuse me, 1.35. Notice how those values are really close. And that's how you know you're doing this right. You actually should get values that are really close. So again, make sure you finish this up. Again, I used 14 washers. You are not using 14 washers, and your moving mass should not be 56 grams. Make sure your numbers are different. So a student argues that as radius gets bigger, the centripetal force and centripetal acceleration should get smaller. Was that the case here? Explain. Well, why would they say that? Well, they know the equations AC equals V squared over R and FC equals MV squared over R. So this should be an inverse relationship. So as far as inverse relationships go, we know that as R goes up, those other numbers, FC and AC, should go down. But let's look at this. Well, what it looks like to me is that despite the radii being very different, the centripetal accelerations and centripetal forces are basically the same. Okay, there's some rounding there, but they're basically the same. Why is that? Well, it's true that there's an inverse relationship here, but this assumes that the velocity is held constant. Okay, so to say that as R goes up, FC and AC go down would be assuming that the speed is constant. Notice here that the speed is not constant. It was 6.08, 3.81. So now I'm asking you to do something a little bit different. I want you to calculate the weight of the hanging mass. So if I have 14 washers, you should be using a different number, 14 washers. And each one has a mass of 10 grams. I'm going to multiply this by my conversion factor. 10 grams per one washer. Number of washers cancels. And I get 140 grams, which we should know is 0.14 kilograms. Now, how do I get the weight? Remember, weight is equal to mg. Fg equals mg. Therefore, 0.14 kilograms times 9.81 meters per second squared. That should give me my weight. Which is 1.37 newtons. Now, what do you notice about the centripetal force and your weight value? You should notice they are very close. Okay, look here. These values are very, very close. They should be the same. So make a comment about that. They should be the same. Okay. And the question is, why are they the same here? Keep in mind, by the way, that this is Fg. This is the force pulling down on the hanging mass, not the force pulling down on the moving mass. All right. So why does this make sense? If we draw a free body diagram for the hanging mass, so here are my washers. We have the force of gravity pulling down. We know the force of gravity is going to be 1.37 newtons here. We just calculated it. And we have tension pulling up. So one thing we should notice here is that this object is not moving. The net force is zero. I'm not going to write some of the force. I'm going to write F net equals zero because it's not accelerating. Therefore, we know that the tension is equal to Fg, which is equal to 1.37 newtons. But think back about what provided the centripetal force. It was also tension. Okay. So what was the agent of the centripetal force? Also tension. I'm just going to write tension. So think about this for a moment. This all starts to make a little bit more sense. This string is one piece of string. The tension in the string due to its hanging is equal to the tension in the string due to its spinning around in a circle. So this all kind of makes sense that the same string will have the same tension.